All right. So now we're moving on from our NRTL coding, and then also in the previous video we talked about coding our azeotrope for, I believe it was ethanol or methanol in water, one of those two. So we had the azeotrope in our binary XY diagram, but now we're going back to our distillation column where we're going to be using something called the Ponchon-Savarit diagram. And this is where now we're assuming that the heat of vaporization does change with composition. And if you remember way back, there was a previous video where we talked about there was constant molar overflow for the McCabe-Thiele diagram. And of course, both of these, the Ponchon-Savarit diagram and the McCabe-Thiele diagram, both of these are relating to binary mixtures only. Um, but the difference here being that now we don't have constant overflow for the Ponchon-Savarit. Instead, we will have to use something with a mass and energy balance such that we can get our flow rates and, of course, our molar fractions. So right here, I just constructed, oh, I think I just copied the distillation column diagram I drew from those previous videos, just so you don't have to waste time watching me draw this out. Um, but yeah, I guess we can just kind of go back to our collab here. So now you see that we have an azeotrope, but actually I believe in the future we're going to be doing instead of azeotrope, we'll be doing methanol and isopropanol. But you'll see that the separation here, obviously with azeotropes or with this mixture in particular, it's very easy to separate here right before you get to about the intersection where the azeotrope forms, again, when the vapor mole fraction equals the liquid mole fraction. So we'll be switching to kind of a more ordinary mixture where it's, well, kind of harder to separate than this azeotrope at lower concentrations for the liquid mole fraction. And doing that will just allow us to code, when we do code our Ponchon-Savarit, there'll be more lines in between, so we'll have a better looking plot versus something that will have easier separation with less stages. So that's just kind of a heads up. We'll be more focused on actually seeing the derivation, the meaning behind the equations for the Ponchon-Savarit, which is right here. You'll notice right from the get-go, there's a couple different things different to our McCabe-Thiele diagram. Now we have, well, liquid mole fraction, basically the composition is the x-axis, but now the y-axis is an enthalpy. So this top curved line and this bottom curved line are relating to the heat of vaporization and the heat of the liquid. Then you'll also notice that there's kind of these dash lines, they're tie lines. So I'll be talking about that more later, but essentially the endpoints of these tie lines are points that are in equilibrium with each other. So if you remember our binary XY diagrams, that's essentially the same information. You'll also notice that we have these 2 points here. We call them difference points, and that will kind of make more sense later. But essentially, they're relating the power that we're putting for our condenser and the power we're putting from the boiler to the liquid mole fractions, or I guess the compositions at the condenser and the boiler. So you'll notice that there's a straight line here and the straight line here. Well, obviously we have the condenser with the more volatile component, numbered here 1, like we always do. And obviously for the condenser, what we're taking out, the distillate mole fraction, is the same as the vapor mole fraction coming in from the stage below. So this would be stage 1. And then for the last stage, we have our reboiler, where now it's not actually, this shouldn't actually be a vapor mole fraction, but you'll see that we'll have to use a tie line, well, actually a mass balance, to get our desired liquid mole fraction from a bottoms composition. So we'll kind of be deriving more of those equations later. So I have some other tabs here. So again, I believe this is more in the future again, but just for my sake, methanol and isopropanol. When I draw these enthalpy lines, you'll notice like the way I draw them, and there's a reason for that. They're not always sloping like this. They can actually be positive slope up or a positive slope down, or not a positive slope down, but a negative slope down. But you'll notice the heat of vaporization will always be higher than the heat of the liquid. And the reason for, I believe for methanol isopropanol, the heat of vaporization and the heat of formation are lower for our more volatile component. So you'll actually see as lines sloping up because it's less negative. So it's technically greater, but we refer to it as less since the heat of formations for methanol is, well, it's lower because there's less bonds. Just looking at the structure between the two, obviously there's more bonds in isopropanol, so there'll be more energy released during the heat of formation. And likewise, since methanol is more volatile, it takes less energy to heat it up to its vapor, so less heat of vaporization there. And I think I just had these comparing the two different vaporizations and formations, but essentially you'll see that they're less than. So yeah, I won't go into detail on this, but yeah, I'll just close these out. And I mean, the majority of the time today is going to be on the iPad. So yeah, I think that's all I wanted to talk about there. So yeah, I guess we could just start deriving. So you'll notice that like with everything we've derived so far, we use a balance. So I guess we can start at the condenser here. Yeah, we can go off to the side here. So maybe something like at the condenser. So at the condenser, we'll do our balance. And we can do something like, so again, vapor coming up, the Y1, I guess it's fine. The Y1 is equal to the distillate flow rate coming out and the liquid molar flow rate coming down from the top stage. So yeah, vapor flow rate V is equal to L0 plus D, essentially. Oops. So I'll go ahead and do that. The vapor coming up for this actually any given stage. So this actually applies to all the rectifying stages that we can say that because they'll be above the feed. That's why they're all the same versus when we switch to the stripping section, that will be different since it'll be based on the boiler. So with the condenser, we have our vapor flow rate coming up from the stage below. And this is actually, you add a 1 since, again, condenser is stage 0, and the stage below is stage 1. So we're adding on a stage. So Vn plus 1 is equal to our liquid coming down. So we're going to say we're at the stage of our condenser, and then plus the distillate flow rate. So now we'll go ahead and do our mass and energy balances, where we do a component mole balance based on our more volatile component. Again, we number that with our Y1s and our X1s. So I'll write it for this line now, but I'll be omitting the one later. So let's do something like, so with our vapor flow rate, we have a corresponding Y1 molar fraction at the N plus 1 stage, and multiply that by our vapor flow rate at the same stage. Same thing with our liquid flow rate. We have a liquid mole fraction, again, for the more volatile component 1, and then at the stage N. So then with the distillate, we have our, distillate mole fraction, the liquid mole fraction at, it's just our distillate. So we use XD to label that, and then we do our enthalpies. So now we kind of have to think about this a little bit in more depth. So we have our vapors. Well, there's enthalpies associated with these flow rates, but we also have to remember that we have a condenser that is taking away heat. So that is taking away heat from the vapor coming in. So I'll be putting that on the left-hand side as a value that we are subtracting. So checking that, okay. So we have our heat of our vapor associated with our that stage of that vapor flow rate at the same stage. And then now I said I was subtracting this value of the condenser, which we can just label as QC. And now you'll notice that QC might feel a little weird since one, it's in, well, and Q is designated as joules per second. This is a energy we're taking out per time, but you'll notice the other units in here with the enthalpy as well. This value is a flow rate times a joules per second, or an enthalpy, so it'll essentially be a joules per mole. So we have moles per second and then joules per mole. So now you have a joules per second. Or I'm sorry, this is joules per second. No, yeah, I believe that should be right. So that should be joules per second. So actually these units do line up. I don't I think we'll see this again. So yeah, essentially at the end I'm kind of spoiling it, but we'll have a joules per mole as well for our this energy being taken out by the condenser, in which case all these other values will also, well, they should be in the same units. So I guess more on that later. And then we keep on going. We have everything else is the same, where we have a enthalpy of the liquid associated with the given stage times its flow rate, and then also a enthalpy associated with the distillate. And technically this is a liquid associated with the distillate, but I'm just going to write that as enthalpy with subscript D, so kind of saves time. And then also I'll be removing the stages from the enthalpies and the mole fractions, just so I don't have to write those out all the time. But remember that we'll be going back to this, I guess, reference point where the vapor is always coming from the stage below, and we are currently basing ourselves on the liquid stage. So wherever that is, that's our reference point. So I guess I can kind of go, I'll do both of them at the same time, since you'll kind of see the similarities as we go along. But I guess the first thing I want to do is, the reason why we're doing this mass balance is that we're using these to get molar compositions at our, our Ponchon-Savarit diagram. And essentially what you'll find is relating these two equations together allows us to get, well, any one of these points that we desire. For the condenser, you'll see that it is the vapor mole fraction, and then for the boiler, the reboiler, you'll see it's the liquid mole fraction. So we're going to try and isolate those based on a relationship that both of these equations share. And to do that, we can get rid of one of our shared variables, so either the vapor, liquid, or the distillate flow rate. For the condenser, I feel like it's easier if we just get rid of the vapor, since we already have, well, I wrote this equation this way. So technically you could do it other ways, but you should have a very similar relationship. But know that the end goal is to somehow relate our distillate mole fractions and our enthalpy mole fractions with the other corresponding values in those equations. So essentially all these points together. All right. So yeah, I'll go ahead and do exactly what I said. We're going to substitute out this vapor flow rate with the liquid flow rate and distillate. So mole fractions, I'm just going to write y times, and now this is Vn plus 1 is Ln plus D. And then this is equal to our liquid mole fraction. And then again, Ln for our liquid stage we're currently at. And I think we should still write the stages for the liquid mole fraction, since it's just one extra letter. And then for the enthalpy balance, we have our heat of vaporization, substituted our vapor flow rate with the same exact thing. And then I'm going to go ahead and move this this energy associated with our condenser to the right hand side. So I'll just put QC here. And then we have added to that our heat associated with our liquid at the same stage, our liquid flow multiplied by our liquid flow rate, and then we have our distillate flow rate, which stays the same. So you'll notice they're very similar in their orientation, and you'll notice that the differences between the two, we want to line those up as well, just to, well, again, we see the differences, and it'll also help us when we're trying to find our intersection point on our diagram that we're solving for those unknown compositions, essentially the balance of the passing streams in our distillation column. And if you remember from the last video, to get those passing streams, we use the operating line and the stripping line. And this is a kind of similar case where we get those unknown compositions with another equation. Well, essentially a balance, mass balance and enthalpy balance. So after this, we can kind of isolate like terms. So I guess let's do this one at a time. So I'll move over the liquid mole fractions here. And then our enthalpy associated with our liquid to the left-hand side. So now we have, well, I don't know, maybe, yeah, sure, why not? We'll do this slowly. So yeah, I'll move those to the, I don't know why I deleted that. We'll move those underlined terms to the left-hand side, and then I'll also distribute out the left-hand side as well. So you can kind of see where I'm factoring things, and I don't just do them too fast. So I'm just multiplying inside, and then I subtract, and the right-hand side stays the same. And then I multiply out again, and then I'll subtract the underlined part. That's a D. And then subtract our liquid enthalpy, or enthalpy associated with our liquid. And this is equal to our condenser and our distillate still. Now you'll see we have our like terms. We have our liquid flow rates and our distillate that is the same. And I'm just going to factor those along each side. Yeah, I won't bother moving over the distillate. Like, I'll just do it all in one go. Hopefully you see the point where we're factoring together our liquid flow rates and our distillate flow rates. That was the whole point of doing our substitution at the start. So we have variables that are pretty much the same for both equations, and so we can relate them to one another identically. So in doing so, I'll have factored out for the mole fraction balance, we have our liquid flow rate is equal to y minus xn, and then we have our distillate flow rate, which is the distillate mole fraction minus, I believe that is y. And again, I'm not writing the subscripts, but no, with y, we designated that as n+1 with our vapor flow rate, the same mole fraction as our flow rate, vapor flow rate. And then what else do we have? We have the same exact thing we're factoring out. So in this case, for the left-hand side, we have the heat of vaporization, and that is minus heat of the liquid. And we also have our condenser again, but we're adding, and then we have our distillate, which is the heat of that distillate minus the heat of vaporization. So now you'll notice I can kind of divide along each side ln over d, and doing so will allow us to relate our, well, the things we're solving for together, so that we have an identical expression, well, expressions that are equal to each other, I should say, between these two equations. So yeah, I'll go ahead and just write ln over d and kind of write them all equal to each other, so it kind of makes sense when we put them side by side. So for our molar fraction, we had xd, and now I'll put in the subscripts back, but remember, I won't put in the component since, again, we're doing this for the more volatile component. But so we have the distillate mole fraction minus the vapor mole fraction, and I believe we designated it as n+1 from the stage below. And then we have, if we move this to the at side, again, I'm just dividing by d on both sides. So on the bottom we'll have, again, yn+1 minus xn. Then of course this is equal to, again, now we do our enthalpy mass balance. So if we divide by d on all sides, we have qc over d plus, and then we have our enthalpy expression at the top, which is our distillate minus our vapor, and our vapor again is at n+1. And then we divide the left-hand side, this side over, So we'll have the heat of vaporization. This is also at n+1 minus the heat of the liquid. Again, this is at the end stage. So yeah, that's our condenser. Um, yeah, I think it might make more sense to just start drawing this, and then we can do the boiler mass energy balance as well, and that will kind of let me transition to the boiler. So essentially, we pretty much know these values based on our reflux. I think I already explained why we're doing the condenser, or I hope I explained it, but again, QC is we're treating it as a positive number. I know in thermodynamics we might have referred to as heat being taken out. Here, we technically, if heat's taken out, we usually refer that as a negative number. But with Ponchon-Savarit, we always describe that, at least the I don't know, the tradition for it in Ponchon-Savarit is to just treat it as a positive number, and whether or not we subtract or add that number is, again, based on the heat taken out or heat put in. So we subtract it, and well, we move it to the right-hand side, which makes it positive. You'll notice as well, all these differences should be positive. Our distillate is higher than the stage below, or any given stage in the rectifying stage, except for the vapor from the stage below, I should say, since to actually graph our plot, we say that the vapor flow rate coming up from, I guess, stage 1 is equal to the distillate mole fraction, and as well as x0, the stage coming from below. So again, that was just our um, our statement that the y1, the vapor mole fraction from the stage below, is equal to the distillate mole fraction, which is pretty much the same as the liquid mole fraction from that stage. So yeah, let's just go ahead and graph this. We can do white. Yeah. So maybe something like fines, and then I'll label like something down here. This is our x-axis, which is just the x1s and the y1s. And then since we're going to be, well, hopefully we'll be doing ethanol isopropanol in the or methanol isopropanol in the future. So the heat of vaporization should be higher in a positive slope. So something like that. So, and you'll notice there's a difference between this difference and this difference, and notice they're not the exact same. That's because for the different components where we have, well, obviously for this diagram, we're showing the more volatile component. So this goes from 0 to 1. So with methanol, there's a difference between its heat of vaporizations of the, well, HV and HL, the heat associated with the vapor and the liquid, versus with isopropanol on the left, where 0 showing that we have no molar fraction of our more volatile component. So technically, well, you can just say that's just 100% isopropanol. You'll see there's a bigger difference there. So that's all that's saying. Again, these depend on composition. So I'll just label this HV and HL. I guess we should move this down a bit since we don't want to mess with that up there. So yeah, I guess we could just start graphing this. Yeah, so we have I'll just write our tick marks just to show where all our fractions are, just to keep me on the same page. So we have some distillate composition here, and we know that is equal to our vapor molar fraction at the top. And I'm writing these on the enthalpy lines because essentially we'll be connecting these points later on. So the next point we're interested in is, well, actually what I should say is that with this y1, we should be able to get, and this should be our x1, with similar subscripts, or I guess the same subscripts, you'll see that, oh, let me just go to the distillation column. So if we have our, again, we got our y1 knowing that it's the same composition as our distillate mole fraction. So if we have our y1, we should be able to get our x1 through the equilibrium stage here. And if you remember what I said earlier about tie lines are the endpoints at which those two endpoints are at equilibrium with one another. So essentially we are able to grab x1 just knowing a1. And that also apply with the boiler. If we know some liquid mole fraction, we'll be able to get a vapor mole fraction. So I don't think this actually goes to 4 stages, but I don't know. I guess we go to 3. Or I guess I can extend this a little bit anyway. Yeah, let's just leave it open for now. So yeah, that's exactly what I meant. So with the y1, we were able to get a some equilibrium, and I'll use that. I'm not good with dashes, so I make it a swirl, and that's just noting that we have a equilibrium between those two. Again, because they're at the same stage, so one's coming from up top, the vapor mole fraction leaving that stage, and one's coming from the bottom, the liquid mole fraction leaving that stage from the bottom. So those are in equilibrium with each other, and we're able to grab that with either using our binary XY diagram, or we can spline these, or I think since we already graphed it in our collab, I believe we used bubble T as again constant pressure, and we graphed those XY coordinates, so it's exact same information there. Now you'll be interested in how we get the passing streams. Again, I mentioned that earlier with our mass balances. If we have our x1 now we're interested in this y2, since that's how we're only able to move on into our next stage here. So to get that y2, well, we have that expression relating a vapor mole fraction and a liquid mole fraction, essentially our mass and energy balance right here. So to do that, we can do something like, so what stage are we on? I guess I should label this too. And I know I'm labeling this, like technically you wouldn't know when you're drawing this diagram. Obviously you'd have to find an intersection between these two equations, and then after you get your compositions before, your x1, your xd, and your y1, those mole fractions, only then you would able to grab your y2. So yeah, I guess while we're at this point, I should also mention something called a difference point, and that's like all the way up here, essentially. So this difference point is what we refer to as these two values. It's our condenser, and now this is what I was meaning to say before. So we had our joules per second, and we had a second per mole for our distillate flow rate, and now we are at joules per mole. That's exactly the expression we want to do, and with enthalpies, essentially that's what I wanted to do as well. But now notice that the right-hand side is completely just joules per mole with enthalpies, since if we were relating our expressions earlier, we had joules per mole and moles per second. Earlier, they were in joules per second. So that was just me getting a little confused with the units. But again, this is our condenser associated with the power of the condenser, that enthalpy associated with our distillate flow rate. So that is called a difference point. And with that difference point, you can they call it a lot of things in different textbooks, but I think in class we use delta R, relating the stripping section. So that's just QC over D. And again, that's a very big value, since that condensing power, is associated with our reflux ratio. Again, our reflux ratio is the reflux we return over our distillate. So if we had something like, I don't know, 5 moles we return per second, with 1 moles per second we take out of our distillate, well, our condenser has to condense 6 moles total of our vapor coming in order to meet that ratio, reflux ratio demand. So that's why we know this value. And again, we also know our distillate enthalpy. Since we're taking out a distillate, we know our distillate mole fraction. We designate that, and we're able to get that enthalpy. So both these values are known, and they are a set value. So that's why it's also easier to just reference it as something else. So we just use delta R here. And notice that this value is going to be very big compared to this enthalpy, since we have to condense quite a bit, which requires a lot of energy. So I'll go ahead and label this delta R, which is equal to our difference point enthalpy of the distillate. And remember that this is a liquid associated, well, it's a liquid mole fraction we're taking out at the top, so you have to use a liquid enthalpy. So yeah, we can go ahead and use our expression up here to get our y2. So to get y2, we're interested in stage 1. So technically n is equal to 1. Yeah, use a different color. Well, I can use the same colors from before. So at n equals 1, we have, what was it? It was our distillate, I believe. And I cannot pick this right color. Okay. So we had our distillate minus our, I believe, our vapor stage. So yn plus 1 right here. And to get that, so we add n as 1, so it's y2, the exact vapor fraction we're interested in. And now we also have yn plus 1 minus xn, so that's y2 minus x1. And remember that everything is known here except for y2. So that's what we're interested in, and we set that expression equal to our enthalpy balance to get an intersection point. And that intersection point allows us to get that yn plus 1 as it crosses our vapor, our two vapor lines with our enthalpies. So we have our difference point. I'll just write that as delta R minus, I should have put these closer to each other. So we have HVN plus 1, so that's our heat associated with our vapor, and we are at stage 2 for that, our vapor coming up from the stage below, and then HV minus HL. So HV minus HL, so the heat of the vapor and the heat of the liquid coming down from above, so that is same as our liquid coming above, so liquid at 1, and then our vapor that is from the stage below, stage 2. Okay. So again, we're trying to find that passing stream molar fraction, and to do that, we'll just relate these two expressions together, find an intersection point. So what do we have first? We have our difference point. Let's use a different color. Our difference point minus the heat of vaporization at 2, stage 2, for our molar liquid vapor mole fraction. So I'm drawing this line here in dots with now I'll actually try with my dash lines, but something like that. Oh, I'm actually getting ahead of myself, but this is, I guess I should label that. So let's do something like, so again, this is man, I don't even know where I left off. I'll just do this first. So this is xd minus y2. You'll notice xd, again, our x-axis is straight across like that. So I can pretty much choose wherever to put that x-axis difference. So we say that's xd minus y2. And then now this vertical height is what I meant to relate here. So that's our difference point minus HV2. And that's why I drew this I don't know, horizontal line. So now we could relate the heat of vaporization at Y2. Notice that's the same value. And now we relate that to our delta R minus HV2. So that's just along our y-axis. So something like right there is our delta R minus heat of vaporization at stage 2. And now for this next part here is where it gets fun. We have our y2 minus x1. So I draw another, you kind of see that we're going to be drawing triangles here. So we have our x1 minus our y2, so right about there. Now you see why I draw those tick marks earlier. And then we have our heat of vaporization at 2 minus the heat of liquid at 1. So again, that's just along our y-axis. So we have at the vapor up here down to our liquid from stage 1. Now you notice these are similar triangles is, I believe, the term we use. And again, similar triangles is something like, I don't know, like the most simple one. So like 3, 4, 5. If we multiply this up, I don't know, is it worth copying this up? Sure. Yeah, let's do it. Why not? So I want a bunch of these. Let's do 3. And then, well, I need 3 more. So 1, 2, 3. And I want to show that these are equivalent, essentially. Well, not equivalent, but you'll notice that their hypotenuse, since it's scaled up, pretty much you multiplied, well, here I multiplied by 3 across, so that's weird. So it's scaled up by 3. I guess I could just erase this. So obviously this is going to be, uh, this is so overkill. But anyway, now we have 9, and obviously this is 12 multiplied by 3. And then we have a new hypotenuse here. That if we multiply by 3, this has to be 15. So you'll notice that these ratios are the same. So it's something like our y over x, our slopes are the exact same. So if you simplify these, I'll just take it as is. So the vertical line is the y-axis, bottom horizontal line is the, or did I say that wrong? Vertical line is the y-axis, horizontal line is the x-axis. So I just write that as is, and you'll notice, obviously, that should be 9. Obviously, these are equivalent to one another since I just multiplied by 3 across. So they simplify to each other, and the slopes are the same, even though the lengths are different. So these are actually similar or what was the word they used in the problem? Similar triangles, yes. So these slopes are actually the same, and now when we draw our line connecting, I think I can actually just draw, or not draw. I can insert a line. I think no. I swear there was you could like insert a shape or something. No, maybe I'm crazy. There we go. Shapes. Draw a line. So we have a line here, and I want to move it. I move it. Oh boy, what is happening? I've never done this before. Maybe something like this. Oh yeah, there we go. So looks like I didn't draw my proportions correctly, but it should be crossing that line. So I guess I can move it over. Why not? I'll actually erase that. Oh no. Okay, that's not good. I'll do something like that and just know that it should actually be there. So yeah, I guess I should have withheld drawing these lines before. So yeah, those are our lines. And eventually you'll see that now we have our y2. Again, we have our y2 right here. So now we should be able to get our x2 here. So that's actually x2. And I guess I can label the other ones while I'm at it. So y3, y4, and x4. So again, this is via equilibrium. And you'll notice now I'm below the feed. And when I'm below the feed now, I actually have to use, well, I can still use the equilibrium, but when I'm below the feed to get these 2 passing streams, now I have to use the, our mass and energy balance at the boiler. So that's exactly what we're going to do. So I'll draw my equilibrium first. Something like this. Okay, my little scribbles. Okay. So now we do actually have to label these with our boiler. So let's just do it down here maybe. I don't have to move that much. Or I could always copy them, honestly. So let's just put them, I'll just put it up here. So this will be at the reboiler. So right next to our reboiler. Debating what colors to use. Okay. At our reboiler. Now this is a different expression. Simply because of the mass balance that we start with. the flow rate balance. So let's just look at it. We have our liquid coming down is equal to our boiler flow rate coming out and our vapor going up. So write that as is. Again, we balance based on the liquid stage, the liquid flow rate, the stage of the liquid flow rate. So we do liquid flow rate n is equal to the vapor n plus 1, the stage coming from the stage below, plus the distillate, or not distillate, the bottoms. I don't know why I said distillate. The bottoms flow rate coming out. Again, we do our mole fraction component balance to the more volatile component. And now I wrote it earlier, I'm going to withhold the subscript 1 since we are understanding we're doing a component mole balance of the more volatile component. And then for the enthalpies, yeah, I won't bother writing the subscripts for those. I'll just write the LNs, essentially the stage for the liquid along with the flow rates. So that will be, so we have now X and Ln, just matching up our molar fractions to our molar flow rates. This is, again, another liquid, their bottoms, mole fraction. And then we also have our enthalpies, which is, let me think, our liquid enthalpy associated with our liquid flow rate. And now we do have a reboiler. So now boilers, obviously you're adding heat to the system. So we add it on the left-hand side. So I guess I should have mentioned this is in equals out. And that's the same thing over here. In equals out, we had our in, which is our vapor, and we took away heat. That's why the condenser is on the left-hand side there. And then obviously out is our liquid and distillate flow rates and mole fractions, also enthalpies. Get the point. So we're going to be adding, and then we use QB for our boiler. And then we have a vapor enthalpy associated with that flow rate, Vn plus 1. And then we have our bottoms, which is just, again, this is a liquid, but I use HB. Again, this is equal to liquid enthalpy of the bottoms times bottoms flow rate. But I just write it as HB for convenience. Yeah, we do the exact same thing, except now it's easier to do it with Vn plus 1 plus B instead of substituting it around and subtracting. Since we do want to isolate, we're going to be subtracting this bottoms composition. We essentially want a similar expression to what we got before, where we're subtracting from our known composition. Oh my goodness. And we're also subtracting from a known enthalpy up here. And obviously for the condenser, we know the liquid flow rate coming down, but you'll see for the, well, we know, I guess I should say that because we know the equilibrium from the stage before, but for the condenser, for the reboiler, you'll notice that now we're trying to solve this since, at least from the bottom, this stage is not, the vapor mole fraction as well as flow rate have no relation to any equilibrium along this distillation column. So the next best thing we have to do is immediately solve for our equilibrium balance. And this is different from what we did earlier, where notice that we actually started with our vapor composition mole fraction, I guess just mole fraction, since that is equal to this distillate mole fraction from the condenser. And obviously that's because they're in equilibrium, they're coming from the same stage. Now we're going to be doing, going straight to our mole balance, or mass and energy balance. But anyways, yeah, we do our little substitution again, with the Ln, our liquid flow rate, and that's just equal to our vapor flow rate from the stage below plus our bottoms flow rate. And then again, this is for the mole fractions, so everything else stays the same. I'll just write y, so Vn plus 1 plus xb, b. Again, our bottoms. Same thing for our enthalpy. We have our liquid, and then we substitute it in. Plus, I'll move it to the other side. This is our boiler energy. And then rewrite everything. So I'll kind of do this in 2 steps now, so I won't have to hopefully you understand the point of us trying to group together our identical variables here, our vapor flow rates, and then that'll be on the left hand side, and our bottoms on the right hand side. So I'll go ahead and do that, I guess grouping like terms like we did before. So if we have our vapor here on the left hand side, what do we have? We have our xn, our liquid mole fraction at the current stage, minus our y. This is n plus 1, but I'm getting lazy. And then we have our bottoms on the right hand side, so bottoms, and then this is our bottoms mole fraction minus our xn. Did I do that right? En plus 1 xn minus y, bottoms xb minus xn. Okay. Then with our enthalpy balance, we do the exact same thing. So this is liquid, enthalpy of the liquid minus heat of vaporization. And then we have our boiler. And then we do our bottoms group-like terms. This is our enthalpy of the bottoms composition and bottoms flow rate minus enthalpy of the liquid. And you'll notice that, again, we do like exact same thing in the expression before. Expressions are, I guess, the mole fractions and enthalpies are grouped in a similar manner. You'll see the bottoms minus the liquid and the bottoms minus the liquid here. Exact same thing with the left-hand side, where we have our liquid minus our vapor, liquid minus our vapor. So that's exactly what we're after. Now we isolate for our vapor over our boiler. And I guess it's coincidental that this is also equal to our boil up ratio. So that was something like this. I guess we could put big N for this the last stage. And then over our bottoms. Is it called bottoms? Is it coincidence that was R? And then there's no R for the, yeah, it's R equals L over D. Reflex ratio is liquid from the stage above over the distillate. I don't know, maybe I'm forgetting something. But anyways, yeah. When we actually set up our column, it's going to be limited in a way that we don't have to set that ratio. It's actually, we'll be setting a recovery ratio, our recovery fraction, however you want to call it, at the top stage. That way we don't have to try to define a distillate mole fraction and mole flow rate. That will get us the wrong answer, something like that would over exceed our feed. We want to limit ourselves to a fraction of that feed and then define everything else accordingly. So that's what we'll be doing. Anyways, getting back to this, use this color. So it was Vn plus 1 over B, and now we'll write all our subscripts back in. So for our mole fractions, we had our liquid mole fraction minus our liquid at the current stage, liquid at the current stage minus our liquid or vapor coming up from the stage below. This is equal to our, so now we have a negative QB over B, our condenser or our boiler energy associated with our boiler flow rate. And this is added to our enthalpy of the boiler minus enthalpy of the liquid. And this is, I should write those subscripts. So bottoms liquid is at N, and then our HL minus HV, which is heat of the liquid at N, and then heat of the vapor from the stage below. Okay. Yeah. And what's important to note here is that these values are actually going to be negative over negative. You'll see that the bottom's flow rate is actually the lowest mole, or not flow rate, the mole fraction is actually the lowest mole fraction for our more volatile component, because obviously we have highest separation at the top. So at the bottom, you're going to have the lowest mole fraction. So essentially it's going to be something like that, where our stages in the stripping section have a higher mole fraction than our bottoms, and then the same thing with the denominator, where our vapor stages actually have more of a molar fraction than our liquid mole fraction, since you'll notice this y1 and this x1, even though they're in equilibrium, the vapor stage is higher in mole fraction, I don't know, saturation than the liquid coming down. And again, that's because this is the more volatile component. That's why it's more saturated in the vapor phase. Okay. So essentially I'm negating everything for that for our mole fractions. But then similarly with our enthalpies, well actually these enthalpies are similar in, I don't know, value, numerical value, since they're both technically well, they both are liquid enthalpies. It's just that liquid enthalpies of the stripping stages compared to the bottom's enthalpy, which is also enthalpy of a liquid. However, this value of this QB over B, this I guess energy associated with our bottom's flow rate, is going to be a very high number, since now we're trying to input enough energy to essentially vaporize all of the liquid coming down. So again, that relates to the ratio of um, our mole balance, essentially what we did up here. So yeah, I'll be negating everything. And then similarly, again, heat of vaporization is just higher than heat of liquid. It takes more energy to vaporize than to condense. So I don't know, how should we just do this? Yeah, I forgot. We should also mention that we have another difference point while we're here. So we'll also want to you'll notice that everything is in terms of differences. So we also want to do that with our numerator in our enthalpy balance here. So you'll notice that I'll subtract something from this value after we kind of invert the signs here. So I'll kind of rewrite it. And now all we're doing is just inverting the signs. So multiplying by -1 across the fraction makes it, well, it's still equal. Since -1 over -1 is just 1. So yn plus 1 minus xn is equal to, and then now I'll put our heat of the liquid up top or in front. Now we want to subtract the value. So subtracting after we invert. So I guess I'll invert it here first. Something like that. HB plus HLN over HBN plus 1 minus HLN. So after you invert it, if we want to subtract, we would subtract HB minus QB over B. Did I do that right? So we inverted it, positive, inverted it, positive. Should be right. Okay. And then we just have the same after we inverted it from the top right hand side. Awesome. Okay. So I don't know. Do we want to start at x4 or can we do x3? Is that okay? Because we can do x4, so that might require a little bit more. We can try with what we have, but I feel like it's going to be not quite enough for our spacing wise. Like remember how I messed up this ratio there? So pretty sure it might be different here. So yeah, I don't know why this is actually okay. So if we follow our spacing from before, x3, x4, and we're hoping that these line up, we have y3, y4. Is there x4? I don't think there is. I don't know why this is x3. I don't know why I wrote x4. Just confusing myself. So x3 doesn't exist. And we're left with something like that. So this is, we could just call this our bottoms here. I don't know why I went out so far. but I probably didn't space it out well enough, but we'll find out. So again, our bottoms, this time it is not equal to this vapor flow rate coming up. My goodness. That's why we have our, I think we can do a balance on that. I mean, let's try, why not? Because we want to say it is n equals 4. So that would be x4, and then you would need, or y4, and you get x3. Do we know that actually? Well, let's just do it. So I'll say n is equal to 4. And if n is equal to 4, or I'm sorry, n is equal to 3. So let's write that out. If n is equal to 3, we have our, let's fine. So x3 minus xb, plugging in n equals 3, we have y4 minus x3. And this is equal to, and I'm going to call this, again, this was the difference point. I don't know, what do we want to call this? Like delta S. The delta S will be like all the way down there again, since the very negative value, again, we're subtracting a lot of energy for that bottoms composition we're taking out. So I don't know, somewhere down here. That might be too far. Anyways, so I'd call this delta S. And delta S was just that expression we wrote. So along with that, we have our HL at given stage 3. So liquid enthalpy at stage 3 minus our delta S. And then same thing, heat of vaporization at the stage above or below, so at 4. And then heat of liquid at the current stage, so 3. So if we try to draw this out, yeah, we should know why 4, since it, again, it's just the mass balance between our liquid components. Or I'm sorry, it is in equilibrium with XB. Is it? Did I draw that right? Guess we'll find out when we try to draw this triangle. Because no, we should know why 4, unless I'm messing things up. No, I don't think we do. Okay. We'll find out. Yeah, let's just graph this. So we have x3 minus xb. Oh, what did I use? I used this blue. X3 minus xb. And that was related to our y4 minus x3. So our y4 minus our x3. So I feel like this horizontal line will be a lot lower, so I'll erase that. This xb minus x3 comes down all the way here. So all this delta S should be matched up with our Euler mole fraction, and then we have the xb minus x3, something like that. And then we have our denominators, y4 minus x3, or I'm sorry, our y-axes, which is our enthalpies. So the liquid at stage 3 related to delta S. And then our heat of vaporization at 4 related to the liquid of 3. So that's like so. Well, there we go. That's our, yeah. So we actually didn't know. So these are our similar triangles. And again, we'll do the same thing. Let me get out my line. And I will bet you that this does not line up. Well, actually, let me draw it. Nope. What happened? Oh my goodness. What is happening? Okay, let me wait. There you go. And then something like That, there we go. Oh wow, I actually lined up pretty well. There you go. And now we got our liquid mole fraction right here. So we draw our equilibrium to third stage. So it looks like we only need 2 lines for each. Wow. Did I mess that up somehow? I guess technically we could get um, x2 related to, well, we could just write x2. But we already knew x2 from our equilibrium from the, how should I say this? The condenser? I mean, we can write it out. I mean, sure, let's write it out. Why not? We can do it for both. But you'll notice that knowing when to switch between the two, if our compositions are lower than our feed, that's when you switch to our stripping section expression. So if we just write this out again for stage at n equals 2, because why not? Just to show an extra red line. So that should be 3, right? Just add a 1 to everything. Equal to difference point, add 1. It's not 1. Add a 1. Add a 1. Add a 1. So we have a difference from heat of vaporization at 3. So that comes out all the way here. And then we have HV3 minus HL2. So that's down here. Or that's enthalpies. I'm looking at mole fractions. So this is XD minus Y3, like so. And then Y3 minus X2 down here. And then we draw our vertical lines. So that's delta R minus heat of vaporization at 3. Something like that. Actually should come down a little more. Like that. And then we have heat of vaporization at 3 minus heat of liquid at 2. So it'll be this line. Again, we draw our nice little line. I will bet you it does not line up. Since this time, yeah, be something like that. So I actually won't draw these lines, you know what? Because they won't line up. But I'm surprised it lined up for the first one, or at least for the first bottoms composition. So yeah, I mean this is our Ponchon-Savarit. I have a feeling if I do it for the bottoms, it also won't line up. So I'll save the hassle there. But essentially, the more stages you have, the more tie lines, the more lines you draw from the difference point, etc. But hopefully, that kind of has. I won't say it's the most nice looking, but hopefully it gives you an idea of what the Ponchon-Savarit looks like and all our difference points. Yeah, I mean, I guess I could label all these expressions here. What did we have? So this was HL3 minus, so the liquid at stage 3 minus our difference point. This was our X3 minus our XB, so the stage above minus our bottoms. Those are both liquid mole fractions. And then we have Y4 minus X3. So vapor mole fraction minus liquid mole fraction from the stage above. And then, what's this Y? So HV4 minus HL3. So heat of vaporization at 4 minus heat of liquid at 3. Why did I throw 3? Is that everything? Didn't write these down. Great. Let's do those. So we had XD minus Y2. So I wrote that in. I didn't do it for the second one, I guess. Which is fine. I hope you get the point. I won't bother to write all those details. So yeah, related all our, we had a rectifying and stripping section mass and energy balances, and we drew intersections between, which essentially is making the equations equal to each other and solve for the unknown variable that we didn't know. And we use that using the expressions to draw similar triangles, and those slopes are the same, so we could connect them, yielding us with the different compositions that we're trying to find. So yeah, hopefully that goes over all the Ponchon-Savarit stuff. Talked about tie lines, similar triangles. So yeah, basically everything boils down to this mass and energy balance. And I believe in the next part we will be actually plotting this up in Python, obviously uh, automatically with some generated functions and whatnot. So all right, if I have nothing else to add, you won't see me after I pause this. So thanks for watching.